I will make a fourth lecture, which will be more a seminar about the possible link between nucleosynthesis and the birth of the solar system. So my first topic will be Big Bang nucleosynthesis. And for those of you who are interested in the history of science, there is this book by Ludwig Selnikier, who actually wrote a very nice and interesting history about nucleosynthesis. And if we think about what people were thinking about this topic in the 40s, there was actually the idea that every element were formed in a single place. This was a dogma, one place for making all the elements belonging to the Mendeleev tables. And there was two ideas about these unique places. Some people thought that all the elements were formed at the very beginning of the universe, in the first 3 minutes after the Big Bang. And another part of the community thought they were formed all in stars, nothing to deal with the beginning of the universe. Today we know that part of the elements, especially the lighter one, are formed at the very beginning of the universe, and most of the heavy elements are formed in stars. There was two prominent figures in this story. One was George Gamow, and George Gamow started from the idea that the universe was much more dense, much more hot at the very beginning. We shall come back to that point when we shall speak about the expansion of the universe in a while. But there was already this idea that our universe had a history, actually, was not every time the same. And since it was very hot and very dense, it could have been that some nuclear reaction took place at the very beginning of the universe. And with his students, Halfer, Hermann, they made the first prediction about the elements formed at the very beginning. They used very not so well-known nuclear reaction rates at that time. And when they did the first computation, they obtained this fantastic, I would say, result that every elements were produced at the very beginning of the universe. And there is a famous paper, authors by Alpha, Bethe, and Gamow. Alpha, beta, gamma. And actually, Hans Bethe was not an author of this paper, but Gamow, who had a sense of humor, relatively well developed, asked him to be a author in order to have alpha, beta, gamma. In the first version of the Astrophysical Journal, beside the name of Bethe, there was a small cross, and below, in absentia. But the editor of APG removed that after that. So this was Gamow. And the other tenant, the one who believed that all the elements were produced in stars, it was a very original mind, Fred Hoyle. He was from UK, and actually he had a very different history about the universe. He thought that the universe was not only, I would say, isotropic, the same everywhere and uniform at each time, but he was believing that the universe was the same at every time. So it is the story or the model of what we call the stationary universe. And Fred Hoyle had very, very original ideas. And very often, his ideas were against the rest of the community of the astrophysicists. And at the end of his life, he said one thing which was interesting. He said that the only idea on which he was agreeing with the rest of the community is that he should have received the Nobel Prize. Actually, he was one of the authors of the Burbidge, Fowler and Hoyle paper of 57. This is a very founding papers about nucleosynthesis. Actually, you will find a very detailed already description of all the nucleosynthetic process in the universe, except the X process, which actually represented the spallation reaction between the nuclear cosmic rays, the galactic cosmic rays, and the interstellar medium. I will not speak too much about this. So these two prominent figures. Who was right neither of the two. And both were a little bit right, actually. So if we speak about cosmology, I would like to refer to one cosmological observation that every of us can do, and which is called, in the literature it's called Olbers paradox, but I would say, as coming from Switzerland, that we should call it the paradox of Cheseaux-Olbers. Actually, this paradox says the following thing. It says that if the universe is infinitely old, and filled uniformly of stars, of galaxies, whatever, in every direction you look, your line sight should end at the surface of a star. A little bit like if you are in a forest, very dense forest, and in every direction you look at, you see a tree. And you can see it in more, I would say, mathematical way. You know that the luminosity of a star decreases with the inverse of the square of the distance. So the luminosity decreased, or the energy that we received is L divided by 4 pi r square, which is the surface of the sphere, and r is the distance to the star. Now, a star which is at a distance small r, all the stars which are at a distance small r can be seen as belonging to a shell whose surface will be 4 pi r square. You can multiply by n the number of stars per unit volume, multiply by dr, the width of the shell, and you will have actually that the luminosity received from all the stars in this shell, n 4 pi r squared dr, multiplied by the flux received by one shell, will be the luminosity received by this shell of the universe. And you can see that the 4 pi r squared cancel. And you have nl dr. And if you integrate over the whole universe, you suppose that the stars have all the luminosity L, of course, that the universe is so old that the light has time to travel from there to here. And if you do the integration over the whole universe, you obtain the infinity. It will be not infinite. It will be a big numbers, actually, because, of course, the stars have a finite surface and they will screen each other. So that, according to this paradox, the universe, the sky during the night should be as bright as the surface of a star. And this is not. So the simple, I would say, observation that the sky is dark at night tells us something about the cosmology, or some properties of the universe at a large scale. It implies that the hypotheses that we have done are not correct. At least one of them is not correct. And I say Cheseaux because Cheseaux was living a little bit, was born in the 18th century, a little bit in the north of Lausanne, near the place where I am living. And actually, he expressed this paradox well before Olbers, I would say. And it's why I think we should call this paradox Cheseaux-Olbers. He has also measured for the first time the altitude of the Mont Blanc, that we can see very well from the place where he was born. He has also made a book about comets. Okay, so now let us come back to modern cosmology. So a first point, a first pillar of the modern cosmology is the observation that our universe is expanding. But what does it mean, universe is expanding? Actually, it does not mean that the matter, the galaxies, which compose the bricks of the universe, are flying away in a pre-existing space. This is not the case. We have not a pre-existing space. We have instead that the space between the galaxies is expanding. The curve, which is very schematically shown here, is a kind of, you see, if you imagine a three-dimensional space where you have galaxies which are uniformly filling this space, at a given time t, the mean or the distance between two galaxies is, let us say, d1. If you wait for a time, at the time t2, it will be, the distance will be d2. and the d2 will be greater than d1. There will be an expansion of the space between the galaxy. It's an expansion of the space, not a movement of the galaxies in the space. And what is represented here is what we call the evolution of the scale factor. It means the multiplication that the distance receives when the time is increasing. It means that from T1 to T2, this multiplication factor will be A, which will depend on time. So it's a constant in space, but not a constant in time. It can vary with time. And the curve is not linear here as a function of time, but it's something which can have some curvature or convex and concave part. And this is the way, this is a scale factor, the multiplication of the distance between the galaxies when time evolves in the universe. We can see a little bit, this is of course very schematic, and I apologize, it's much too simple in some way, but you can see the galaxies has some points which are drawn at the surface of a balloon with increasing in radius. The galaxies which are drawn on the surface of this balloon are not moving. This is the space which is moving. And if you have a galaxy which emits a photon at a given time, t1, this photon, during its travel to us, will also, I would say, feel the expansion of the universe. And during its travel, if it at the beginning its emission or its wavelength is lambda 0, due to the fact that this photon during its travel undergo the expansion of the universe, its wavelength will increase when it arrives to us. So there is a phenomena which is called redshift. The wavelength will decrease during its travel from the galaxy to us. And this redshift, we can measure it. And this is a fantastic point. So I think that every of you know what is a spectra. We can take the light of a galaxy. We can decompose this light in its different wavelengths or frequency or its different colors. And we can find some colors which are missing, which are due to the fact that some photons are absorbed by constituents in the galaxies, sometimes in the interstellar medium too, or intergalactic medium too. But you have these lines which are corresponding to the interaction of light and matter at very precise wavelengths. And what is shown here is above the spectrum of the sun, where you have some, for instance, double lines. I don't know exactly. It can be due to the sodium lines, for instance, or to iron lines. And you know that these lines have perfectly well-defined wavelengths. If you look at a faraway galaxy, you can identify this same line. And you see that here, for instance, in that galaxy, the doublet that is here, accompanied by the single line here, are slightly shifted to the red. So you can put here a wavelength, which is the wavelength received from these galaxies, that we can call lambda received, wavelengths of the lines received, and you can compare with the lambda of the line if this galaxy was at the place of the sun without moving with respect to us. And this difference between the lambda that we receive and the lambda of this line at the emission is called the redshift. So by analyzing the light, you can relatively easily compute this redshift. You have to identify the line, an iron line at, let us say, 1,500 or more, 4,000 angstrom, for instance, and you observe it at 5,000 angstrom. So it means that there is a delta lambda over lambda, because very often we measure a relative increase of the wavelength, which will be 1,000, the difference, divided by 4,000, the emission line, the wavelength at the emission. As I said, we can define in the universe the scale factor. The scale factor is here defined as the letter A. And at a given time in the universe, we define the scale factor, so at a given time, which is TE, for instance, here, as the relative difference between the mean distance between galaxies at the time TE and the mean distance of the galaxies today. In the past, the universe was smaller. So it means that RTE, which is the mean distance of the galaxies at the moment of the light started, was smaller than today. Because, of course, the light took some time to come from the galaxy to us. And so A is a quantity which will be smaller than 1, because we look in the past. In the future, it will be greater than 1, because in the future, but we cannot see in the future, the distance between galaxies will be larger than the one they have today. So this is just a definition. And as I said, this is the wavelength of a line that would be the wavelength that you measure in the laboratory. And this is the wavelength of the same line. So you know it's, I would say, wavelength in the rest frame reference. And this is the wavelength of the same line observed in the galaxies. And these galaxies actually emitted this light when the universe was smaller, because there was some time for the light to travel from the galaxy to here. And this ratio, actually, it can be shown, I will not show it, but it can be shown that measuring this ratio, actually you can obtain this quantity, namely the scale factor today to the scale factor at the time of emission of the galaxies. Or it is inversely proportional to the scale factor that we have defined above. I will not demonstrate here, but I will like that you understand, or you appreciate this puzzling fact that measuring difference between wavelengths gives you an information about the way the whole universe is expanding. This is absolutely incredible, I would say. I must say also that, of course, this is much simplified, because there is a lot of intricacies. You see, the first one is that the movement of expansion is unfortunately not the only one. You have sometimes some galaxies which are falling into a cluster of galaxies. And of course, this will produce some disturbance. This fact becomes more and more true when you look at far away, because far away you are dominated by the expansion and not by, I would say, peculiar motion of the galaxies. But this is fantastic. Measuring difference of wavelengths gives you an information about the scale factor in the past of the universe. Very often in the Hubble laws, we relate this redshift to the distance. And actually, we can imagine that farther away is a galaxy, more time the light has taken to come to us, and so we see a universe which was smaller. You see? So there is a relation between the redshift and the distance. Larger is the distance, larger is the redshift, because this term here will be greater, I would say. So the distance, how we measure distance in the universe, it's, of course, we can do a whole lectures about this topic. The first point I would say that, of course, when you look at the sky, you look a two-dimensional plane in some way. You have no hints by looking with the naked eye about the distance of the things. It's a little bit like if you had a kind of ceiling where stars are just, I would say, glued over some surface. You have no way of having an hint about the third dimension. And we could, I would say that a great part of the history of past astronomy has been to find ways of exploring this third dimension, to obtain distances. To obtain distances, there are some, I would say, not trick, but some methods which are based on the fact that you need to make the two techniques at a given point overlap. What I mean, this is the concept of the distance ladder. The first techniques to obtain distances is the techniques of parallax. And actually, it's a very easy technique to see if you put your fingers in the front of your nose and you look at your finger with one of the eye and the other, you will see that your fingers will be in front of two different persons here. You see, I will see my finger is not moving, but it is the point of view which is moving, and I will see my finger in front of different part of the background landscape, if I can say that. And you can see that this apparent movement of vibration of my finger will increase when the finger is very near my nose and will decrease when I put it very far away. So I will not ask you to do the experiment now, but you can do it. And this is actually, you can do the same by, of course, if you are using a star with the left and right eye, it will not change much because the star is much too far away. But if you take the orbit of the Earth around the Sun as actually your two eyes, you look at a star at, let us say, in March of this year, and you wait 6 months, you will be on the other side of the Sun, so there will be a distance between the two positions of the Earth of about 300 million of kilometers, 2 times the distance to the Sun, and you will look at the same stars. You will look a slight difference of position with respect to stars which are much far away. And this is the effect of parallax. This is the effect of parallax. And this can give you a very precise distance which has no link to any model. You see, it's just geometry. You can use trigonometry and you have a distance. But of course, you can apply this way of doing only for a small volume around the Sun. After that, you need something else. And this something else will be the Cepheid stars. You know that Cepheid stars are stars which are beating like a heart. They are growing in dimension. They are, I would say, becoming smaller, growing again. And they are doing that in periods of about a few days or 1 day. And Miss Hewitt found a very fantastic correlation between the pulsation period of these stars and their true luminosity. It means that more luminous is the Cepheid, longer will be its pulsation period. So you can look at such a stars, you make what we call a light curve. So you draw the evolution of the luminosity of the star as a function of time. And you will see that there are peaks, there are minima, maxima, and so on. And you can compute the period of this beating. So you have the period. And from the period, you have the true luminosity. And from the true luminosity, you can have the distance by comparing with the apparent luminosity. But the true luminosity, you can have it for those Cepheids for which it's possible to obtain their distance through the parallax techniques. So you know the distance, so you can go from the apparent luminosity to the true luminosity. And this is what Miss Hewitt did. And then you can use much farther away Cepheid, for which you cannot use parallax because they are too far away. But since now you have this relation between P and L, you can apply the relation and get much more information about distant parts of the universe. So it's a way, you see, you need, in order for this to work, that to have some Cepheids for which parallax techniques is possible. And then you can construct this period luminosity relation from empirical data and use it, saying that, of course, you have to make the assumption that the Cepheid that you use far away are the same that has been used to make the, I would say, the calibration curves. This is, of course, an assumption, and sometimes it can be tricky, I would say. And then if you want to go even further, you will need other sources using more or less the same, I would say, principle, that are what we call standard candle. And one of the most famous standard candles present day is what we call type 1a supernovae. Type 1a supernovae comes from I would say, the fact that you have probably a white dwarfs, which by accretion, white dwarfs is a star which has more or less the mass of the Sun, and which has a radius equivalent to the radius of the Earth. So it's a very dense star. 1 cubic centimeters would be a mass of about 1 ton. And these stars are sustained thanks to the derivative pressure. And these white dwarfs sometimes cannot have a mass above some mass limit, which is called the Chandrasekhar mass limit, which is around 1.4 solar masses. Above this mass, the white dwarf will collapse. And this collapse will produce nuclear reaction that will completely destroy the star and produce, by the way, a lot of iron. Most of the iron in the universe and most of the iron which is in your blood comes from this type 1a supernovae event. It happens that these supernovae are more or less always the same luminosity at their peak. You see, if you draw the luminosity as a function of time, it will go very high at the beginning. It goes to a maximum value and then decreases. And this maximum value is nearly the same for every type 1a supernovae. It's not exactly. There is some also intricacy here. And so it can be used as standard candles. So I will not go too much further away here, but you can then obtain a relation between the redshift, which is here, and the distance. And actually you have two curves here, which is a little bit tricky to explain. But you see, if you have galaxies at this distance here, actually this curve is obtained, or let us say a galaxy which has a redshift of 10. So there is a big difference between the two wavelengths. The photons started from that galaxies, and during its travel, its wavelength has been increased by nearly a factor of 10. But this curve indicates how long the photon had to travel to go from this galaxy to our position at redshift 0. And it will be about 13 billion years here. The other curves tells you where is the galaxy today, in case it would be possible to measure the distance between us and these galaxies at the same moment, at the age of today of the universe. Because of course, if you are a photon, you are starting in this direction to join the telescope on the Earth, but the galaxy is moving on the other side. In the meantime that the photon has made the travel towards you, the galaxy has also traveled in the other direction due to the expansion of space. So actually, you see, this would be the time that the photon has taken to come to us, and in that time, the galaxy had gone much farther away. It shows a point that the notion of distance becomes a bit tricky. Actually, when you measure a distance, you measure two things. You measure the distance at the time when the photon was emitted, plus the distance that the universe has expanded during the flight of the photons. At the beginning, of course, for very small distance, these two quantities are very similar. And actually what Hubble measured, actually you see it's 10 million, 10 gigayear. This will be 100 million years. This will be 10 million years. And actually the distance over which Hubble made its first measurement was 2 megaparsec. It means 6 million years. So it's a little bit of this curve here, you see? The first Hubble measurement, a little bit here. Okay. So this is the Hubble laws. Of course, if you want to make a history of the universe, to introduce time, because actually the redshift tells you, a redshift 10 tells you that when the photon was emitted, the distance between the galaxy was 10 times, about 10 times smaller than it is today. But there is no time no age. In order to have a time, you need to inject physics into the models. And of course, here I cannot go too much into the details. It's also not my specialty, I would say. But actually, you need the general relativity. You need these equations, which are called the cosmological equation. One is based on the conservation of the energy. The other one is based on the movement equation. And you need an equation of state. For those who are interested, there was McCree and Vitti a long time ago who actually succeeded in providing some classical view of this solution, starting from the Newtonian gravity. But I will not comment on this. What I mean here is that if you believe the people doing physics, it's possible, making, of course, some assumption about the universe, about its content in energy, in energy, yes. You can obtain a way over which A, the scale factor, vary as a function of time. When you do this, and actually it's what Gamow did in his work, when you do this, you can obtain evolution of the temperature, of the density as a function of time. It's a bit complicated diagram. I will not go too much also into the details, but there are three things that you can retain. The first thing is that during at least the part that is of interest for us, the nucleosynthesis, the Big Bang nucleosynthesis, most of the energy in the universe was in the photons, in the radiation. It is why we call this era the radiative-dominated era. The second point is that the temperature was decreasing, and was decreasing with the scale inversely to the scale factor. Actually, we have a kind of O1, if we speak about cooking and nucleosynthesis as a cooking recipe. We have a O1, which is the universe as a whole, whose temperature is decreases with time because it is expanding. R is increasing, the temperature is decreasing. And you can see that the models show this decrease indeed. And the third point is that the decrease is relatively fast. Actually, I've given you here a simple relation, but which is relatively reliable, which gives you the time as a function of A. You see, A becomes larger and larger, so the time increases as a function of the expansion of the universe. And you can attach to each value of A an age of the universe. So, the point is that you have high temperature at the beginning of the universe, but this temperature is decreasing. And it's probably why you can only produce part of the cooking of the elements. Because it's a little bit like if you put a cake in the raw one, but you are limited in the time of hot temperature. And so you can do only a little part of the play, of the game. Maybe an interesting relation, because if we can start from the question, what are the temperature needed to make an element? Actually, as you know, an element, for instance, like helium, has some kind of binding energy. What does it mean? It means that if you want to destroy this element, you have to provide this binding energy to remove the two protons, the two neutrons apart. But as you know, in physics, we have conservation of energy. This is also the energy that has been produced when the two protons and the two neutrons collide or merged or reacted in order to make a helium atom, a helium nuclei, I would say. Because here we speak about nuclei because it's so hot that there is no neutral atoms at that time. So the binding energy of a nuclei is around mega electron volt. And in order to have photons of this energy, you need temperature of 10 to the 10 K. So 10 to the 10 K is the temperature where the photons have energy equivalent to the binding energy of a given atom or of a given nuclei. Of course, it's a very rough every nuclei have different binding energy. But this is just an estimate, an order of magnitude estimate. So, if you want to know, this temperature, let us say, of 10 to the 10 K, mean that if you are above this temperature, this nuclei can be destroyed by the photons. If you are below, it means that this nuclei can stay without being destroyed by the photon in some way. So if we take this temperature, let us say 1.2 10 to the 10, and we look at what was the scale factor. Actually, this temperature, as I said, are the temperature of the photons, of the radiation. And it happens that we know the temperature of the photons which are in the old universe today. We know this temperature. For this, I have just to make a small parenthesis. It's about a concept which is called the cosmic microwave background. I have not prepared a slide about this, but just to give you what it is, we can explain the following points. At the very beginning of the universe, you have this very strong connection between the photons and the matter. If you are a photon at the beginning of the universe, you will interact a lot with the matter. Actually, what we call the mean free path, the distance that the photons can fly between two interactions, it's much less than the dimension of the universe. So it means that the photons are constantly emitted, diffused, reabsorbed. They are playing together with the matter. It's why at the very beginning of the universe, you have a unique temperature for the matter and for the radiation. Now the universe is expanding. And expanding means that the density of the matter will decrease as a function of time. At a given point, also, the matter will change of nature. It will become neutral. But anyway, at a given point, due to this expansion of the universe, the photons will begin to react less and less with the matter. And at a given point, they will completely divorce from the matter. They will have their own life without speaking more to the matter. And this happens about 300,000 years, 400,000 years after the Big Bang. There is this phase of decoupling where the photons became, I would say, independent of the matter. And from that time on, the temperature of radiation and temperature of the matter was different. But this temperature of the radiation today, we can measure it thanks to this radiation, which is inside the whole universe and that we call the cosmic microwave background. And this radiation has today a temperature of about 3K. So you see that the temperature varies as 1 over A. So you can say that A, at the time of nucleosynthesis, when the photons, or let us say the scale factor when the temperature of the radiation was 10 to the 10, can be written as 3, the temperature of the radiation today, divided by the temperature when it was 10 to the 10. And it is about the universe was 10 minus 10 times smaller than it is today. And thanks to the second relation, we can have a time by putting this value inside here, and we have a few seconds. So you see, it's the way Big Bang nucleosynthesis is working, by using this kind of relation. You can, thanks to these two relations, know the temperature that you have at different time. And you can, of course, bypass, you can replace A by the temperature, and so to have this formula here. So here you have the age that is given, that corresponds to the universe when the photons, and by the way also the matter, because they were combined, had a given temperature. So here you can do the same, of course, for other quantity like the density. And so you can do nucleosynthesis with that, because you know how the density is and temperature. You have to know also how the chemical composition is varied. Now I come back to my question. at the beginning, you know, there were these two tenants. The one who said all the elements were produced in stars, and the other who said all the elements were produced in the Big Bang. This small computation tells you that at least one element, which is here helium, cannot be made by the stars. It's an order of magnitude, but how does it work? When you are transforming 4 protons into 1 helium, each time you transform 1 gram one proton, not photons, I don't know what I said. Each time you transform 1 gram of hydrogen into helium, 0.007 gram is transformed into energy. So it means that the quantity of energy that you released will be the quantity of hydrogen transformed into helium, that I call delta M, multiplied by c squared. Now, delta M, if I speak about just the production of 1 helium atom, you need 2 protons and 2 neutrons for 1 helium atom. So the gram will be 2 times the mass of the protons plus 2 times the mass of the neutrons. This will be the quantity of gram that are involved into the reaction. And you will take 7,000 of this total mass, because it is only that part which is transformed into energy. And you get this quantity, 0.028, the mass of the proton multiplied by c squared. Actually, you can transform, of course, you can put the mass of the proton, the velocity of light, and you obtain this quantity of energy, 26 MeV, mega electron volt. So this is the quantity of energy produced by the synthesis of 1 helium atom. Now, you can look at how much of energy has been emitted by stars in our own galaxy, the Milky Way. So you have to take the luminosity of our galaxy multiplied by the time during which our galaxy had this luminosity. So you can take a value L, which is more or less constant, and you say that in our galaxy you have about 10 billion of stars like the sun. So 10 to the 10 solar luminosity. So this will be L. And you suppose that the luminosity or the galaxy has had this luminosity for about 5 billion years. It's a bit, I would say, kind of orders of magnitude, I would say. And you obtain these numbers here, which is the energy emitted by our galaxy during the 5 last billion years. How much nuclei of helium have been produced? So you have this quantity, which is the quantity of helium being produced, which is the total energy released divided by the energy released by the synthesis of 1 helium atom. So this is this quantity here, the total energy released, divided by the first one, 4.2, 10 minus 5. And you have these numbers, 10 to the 65. This is the number of helium atoms produced in order to satisfy this energy output. Of course, here, implicitly, you assume that all this energy output is due to nuclear reaction, which is more or less correct, I would say. So you can compute the mass of helium that you have produced. You have to multiply these numbers, which is produced by the mass of 1 helium atoms. This is a mass. And you can make a relative value here, because very often in the universe we express the abundances as mass fraction. So at the beginning, the galaxy was made of about 10 to the 10 solar masses of hydrogen, and part of it was transformed to helium. And so at the end, you have a mass fraction of helium, which is around 10%. This is below what we observe. Actually, today, in the sun, for instance, we have 27% of the mass of the sun, which is made of helium. And here you obtain 10%. And actually, this number is probably an overestimate. And if I ask you, what could be the things or the features which make these numbers overestimate? Actually, we can at least say 2, I would say, possibilities. First of all, we suppose here that all the helium that has been produced in stars has been re-injected into the interstellar material. But some of it can remain locked into the star, for instance, into white dwarfs. Some of them can also be produced by stars, but then helium can be used to make carbon and oxygen. So some helium also can be destroyed by stars. This we have not accounted for in our, I would say, very simple estimate. So these two first factors tend to say that we have largely overestimated helium. The third one is maybe something that can say that we have maybe underestimate. Actually, the Milky Way has an age more of 10 to the 10 rather than 5, 10 to the 9. So we have taken half the lifetime. Of course, we don't know what was the luminosity in the very early phase of the galaxy. But anyway, this can be a factor which say that we have underestimated. But what we know today, when we are doing much more sophisticated, I would say, computation, we know today that the stars have contributed only to 2–3% of the mass fraction of helium present in the present-day universe. Most of it was down in the Big Bang nucleosynthesis. Okay, so just to give you a few nuclear reactions. Actually, I think for me it's a little bit boring to make a whole catalogue of nuclear reaction anyway. I think this is not to say that it's not an interesting topic. It's a very interesting topic per se. But I think it becomes interesting when you are doing the work yourself. You see, when you are just speaking to people, just to make a list of nuclear reaction is not so pleasant. So I give you just a few points here. The first reaction, which is important in Big Bang nucleosynthesis, is a reaction between protons and neutrons, which produce deuterium. But deuterium is a very fragile element. So you have this idea that in order, you see, you have proton, neutrons, which produce a deuterium, but if you are too hot, deuterium is completely destroyed, and you have again deuterium, which is producing protons and neutrons. In order for this deuterium to survive a little bit and to allow to capture other proton, neutron, to go a little bit higher in the higher mass range, you need to be below some temperature. And actually, you need to be below a temperature which is below the binding energy of deuterium, which is 2.6 10 to the 10 K. And so this is where deuterium can survive and where you begin actually nucleosynthesis in the universe. And what I said is that, of course, this is just the beginning. In order for deuterium to accumulate at a sufficiently high level to allow to go further, you have to wait a few times, and this is about 270 seconds after the Big Bang. You can make very simple estimate without doing any computation. Actually, today you can ask, at least in physics, you can give as a practical work in the third years in physics to write a little code for Big Bang nucleosynthesis. But of course, when the first did that work, it was really a big achievement. Today, it's relatively easy to make a small, of course not precise one. If you want to do precisely, it requires much more sophisticated code. But it's not a very complicated problem because you have one zone. It's not like a star. In a star, you have a lot of temperature, a lot of density in each shell of the star. In the universe, you have one temperature, one density, one chemical composition at every time. So it's a relatively, I would say, it's a one-zone model if you want. But anyway, you can even do much simpler. You can say, you can first, a very important point is to compute the numbers of neutrons to protons, or inversely of, number of neutrons to the number of protons. Actually, as you know, the neutrons are unstable particles. It's only when a neutron is inside the nuclei that it is stable. But if it is alone, if you wait about 15 minutes, the neutrons, or most of the neutrons, because it's statistical, will decay into protons. Neutrons will make protons and will eject positrons, and a neutrino, electronic neutrino will be also released. And actually, you can compute for every temperature the numbers of neutrons to the number of protons by using this formula. And this formula tells you that you have here the difference of energy between the neutrons and the protons, which is about 1.2 MeV. And here you can compute it for different temperature. Now, if you have photons, let us say, now it happens that yes, if you take a temperature which corresponds to 0.6 MeV, because in order for a protons, you see, at a given point, you will have neutrons and protons, which will, I would say, transform each other. The neutrons can, for instance, capture positrons to become a proton, and the proton can capture an electrons to become a neutrons. So you have some interchange between the two. But for this to occur, you need to have positrons and protons. And this positron and protons comes from the decay of photons. Photons can produce positrons and protons. And the energy needed for making one electron is 0.5 MeV or 0.6 MeV, 0.5 MeV. And in order to make a pair of electron and positron, you need 2 times this energy, which is about 1 MeV. So you can actually, yes, I have indicated proton plus electron, it gives neutrons plus electronic neutrinos, and neutron plus positron gives protons plus anti-electronic neutrinos. But in order to have this kind of interchange, you need electron and positrons, and electron and positron can be formed by transformation of photons. It happens that when the temperature of the photons becomes below 0.6 MeV, there is no longer pairs of electron and positron which are formed. So there is no longer possibility to make interchange. And this froze the ratio of neutrons to protons. And this freezing temperature around kT equals 0.66 MeV. And so you can compute this freezing ratio, which is about 0.135. So once you have got this result, you have this kind, of course, this is just orders of magnitude. You have different way of approaching this, but it's correct. It's a correct order of magnitude. It will not be 0.5. It will not be 0.01. It will be around 0.1. When you have this ratio, you can compute the number of deuterium that you obtain, assuming that all the neutrons that you have will be used to form deuterium. And you can compute this ratio, the number of deuterium divided by the number of deuterium plus the number of protons which have not been used to make deuterium. So these are the total numbers of particles. And the number of deuterium, since in one deuterium you have 1 neutrons, 1 protons, the number of deuterium will be equal to the number of neutrons. You have the numbers of neutrons because it's equal, and the number of protons which are not inside deuterium is the number of protons minus the number of neutrons. Because we have, each time you have a deuterium, you have 1 proton and 1 neutron which is used. So you do, and you obtain that the number fraction of deuterium will be equal to this frozen ratio between neutron and protons, at mean 0.135. So at a given point in the Big Bang nucleosynthesis, you will have a fraction numbers of deuterium which is 0.135 or around 0.1. You can do the same for the helium. You can say that all this deuterium will be used to produce helium. I will not go into, you can look at yourself, you can convince correct. Actually, I corrected yesterday night because I made an error. But if there is an error, please tell me. I will correct my view graph, but I think it's correct. But I will not go. It's the same idea. In that case, the number of helium will be half the number of deuterium. Because to make 1 helium, you need 2 deuterium, because it's 2 times protons, 2 times neutrons. So you can do it, and you obtain, this is a bit too much, but you obtain that the fraction of mass would be 0.28. This is even a bit larger than what we need, you see? So we see that with a star, we produce much too less. And with Big Bang, we are in the correct order of magnitude. So helium is produced mostly by the Big Bang nucleosynthesis. So I will go a little bit more rapid now, because I would like to finish these first lectures. Actually, what is fantastic is that if you would be able to measure the helium at the beginning of the universe, you will have a kind of constraint on this Big Bang nucleosynthesis. But it's not easy, of course, because we have not piece of the beginning of the universe, at least nearby us. And you have to look at very far away galaxies, or also galaxies which have a very low content of oxygen, because oxygen is produced by stars, and if you have less oxygen, much less and less oxygen, you are nearer and nearer from, I would say, primordial abundances. And this is what a colleague, Yuri Izotov, with Tuan, who is working also in Paris, they have made this kind of measure of helium in very metal poor clouds. And so they got some value for the primordial helium. I will just come back. If the nucleosynthesis which occurs in the early universe involved only a small numbers of elements, only the lighter one. And here you can have a look if you want. This is the time, and you have the abundance of the elements, which is varying with time using the way the temperature, the density, and the composition vary as a function of time. I will not so much go into much detail here. But there is a point that maybe is interesting to mention, is that you only produce light elements. And why do you produce only light elements? Of course, the first reason is because the temperature is decreasing. So the whole one is becoming cooler and cooler. So you need hot temperature for longer time in order to produce all the elements. And the second point is that you have no stable element with atomic mass number between 5 and 8. Actually, all these elements have a very short lifetime. They are, I would say, they disintegrate very rapidly. You see, if you take one helium and one helium, it makes barium-8. And after 6.7, 10 minus 17 seconds, beryllium-8 disintegrate again into alpha. So you have a kind of bottleneck here. And actually, it will take some time for Salpeter to discover triple alpha reaction, and for Fred Hoyle to make a fantastic deduction that I will come back in the third lectures. The point is that you can make very relatively simple models of the beginning of the universe. It's much more simple than some other, I would say, large-scale model for the universe, because at the beginning it was dominated by radiation, and it makes a lot of simplification. So you are relatively on strong basis here. And when you do computation of the Big Bang nucleosynthesis, you see that the results depend mainly on 3 parameters. 2 of them are more or less well known today. The 2 which are more or less well known is the numbers of family neutrinos. We know that there are 3 families of neutrinos, thanks to experiments made at CERN. And there is the lifetime of the neutrons. There is still some discussion, but it's relatively well-known numbers, actually. But there is another parameters, which is not so well known, I would say. But fortunately, it makes the results to vary a lot when we change these parameters. And this parameter is the number of baryon. Baryon are common day, or the common matter, I would say, protons, neutrons, and so on. And the number of baryons divided by the number of photons in the universe. And if you take, for instance, just this plot as an example, you have variation of this quantity. This is the number of baryons to the number of photons divided by 10 to the 10. This is eta 10 is equal these numbers divided by 10 to the 10. And you vary it, and you look at how much helium you produce, you see? What is extraordinary is that, of course, you see the two blue lines correspond to what Isotov and Tuan has obtained by looking at very, very primordial material, or I would say oxygen-poor cloud. And you see it's relatively large. And actually it spans a large range of this quantity, number of baryon to photons. But there is one element which gives a relatively precise answer, and this is deuterium. Deuterium is really a biometers. The measure of the quantity of deuterium produced at the very beginning of the universe gives you a hint of the numbers of baryon in the universe with respect to the number of photons. This can be seen in this middle diagram. You have again the number of baryon to photons, and the upper curve corresponds to deuterium. And you can see that deuterium decreases a lot with this quantity. I remember that helium is between 0.24 and 0.25. It's 0.01 the amplitude. Here you have a factor between 50 to 5 or less than 5. So you have a much greater span. And you have the green line which corresponds to the observation which are done by looking at the quantity of deuterium in very far the galaxies. And you obtain a value here which is 6. So you have the number of baryon to the number of photons, which will be 6 10 to the 10. And actually, the black line here corresponds to what has been obtained by another way of computing this number of baryon to number of photons, by studying the cosmic microwave background by the Planck satellite. And poof, it goes right in the good place. So I must say, it's really amazing. It's amazing. Okay. Just 2 points now. The first point is that Big Bang nucleosynthesis is one event in the very early universe. You have many more than that. But of course, I am not here for speaking a lot about this. You have to maybe to retain that this Big Bang occurs during the first 3 minutes after the Big Bang. What we have at the end is not a lot. You have, of course, hydrogen, you have helium, helium-3, you have lithium. Lithium is a very, I would say, problematic element because in contrast to deuterium, it does not fit well with the observation. But there is something else with lithium which is probably due to something which occurs in the stars, you see. Because when you look at the evolution of an element, especially when you look at this evolution of the element inside the star, you have to account for the fact that this element can be destroyed in the stars or can be produced in the stars. So you have not a lot at the moment. And as Sylvia Ekström, I think, said, starting from nothing and having only 15 minutes ahead, one cannot achieve great things.